Did you know that Netflix analyzes billions of frames of every TV show and movie? And using all these frames, they can do incredible things. In today's video, I'm going to show you 3 things that you didn't know that they could do with these algorithms. Netflix. It's known for its innovative tech stacks and state-of-the-art engineering to power everything that they do. And funny enough, it actually started this way when they first got into the business by shipping DVDs physically to your door.
Go to Netflix.com, make a list of the movies you want to see, and in about 1 business day, you'll get 3 DVDs. Keep them as long as you want, without late fees.
The co-founders, more specifically Reed Hastings, was a computer scientist who co-founded a company that built software to debug Unix software, which ended up being sold for $750 million. Whatever his cut was, he used to fund Netflix. So from the start, we had a computer scientist that started Netflix with his own money. It's almost like it was always going to happen. Netflix just focusing on the tech of TV and film. One of these areas of innovation would be computer vision. But before we even talk about computer vision, let's first talk about the first algorithm by Netflix, the match cut transition. When editing a movie or a trailer for a movie, how do we transition between 2 completely different scenes? To understand this, we need to understand how our eyes analyze something on the screen. If we take 2001: A Space Odyssey, our focus stays on the bone as it's thrown up. Now, composition-wise, we only see the sky, so clever filmmaking would be to cut to the next scene that follows the structure immediately. So we understand what happened almost immediately. Our eyes don't have to play a game of catch-up. Now, if you're making the film or TV show, you can plan for these shots to be made. But how can Netflix do this when going through tens of thousands of movies and TV episodes, up to 2,000 shots each? We need to automate this. But how do we even get a computer to understand what is on the screen? Netflix engineers comb through thousands of hours of video to do a more common type of match cut. This is called frame matching, where the framing of a person is well defined. So they decided to use a machine learning algorithm, yes, machine learning, not everything is AI, to do something called instance segmentation. Now, our eyes can easily look at this photo and see the ground, the dog, the person, the water, the sky. But how do we train a computer to identify this? Instance segmentation is exactly what it sounds like, which pixels belongs to the human, etc. And before we had all this crazy AI and machine learning type of things, we had to resort to good old-fashioned mathematics. For example, the Viola Jones framework was actually pretty clever in detecting faces by patterns in the lighting of your face. And methods like this were great for specific objects, but you can take a picture of anything. So you don't want to build an algorithm for each individual item that you take a picture of. In 2015, fully convolutional networks for semantic segmentation by Long, Shellhammer, and Darrell showed the first end-to-end deep learning approach to segmenting at the pixel level using a skip architecture. A convolutional neural network is like a gigantic pipe with a billion filters through it. You put the thing that needs to be AI'd at the top, and it will output what the training wants it to do, like detecting if this image is a bird. But for segmenting items in a picture, you need a lot of data and a lot of context to fully understand the whole picture. So where this skip architecture comes in is that it's able to get the final result, a dog, but also gather context about items and edges from previous steps. And of course, AI has skyrocketed the last 3 or 4 years. So we even have up-to-date models like Segment Anything 2 from Meta. So Netflix went through their giant catalog, segmented the main person of interest in the shot, and then computed the intersection over union to see how it would look in the match cut. And at first, the focus was only on human characters, but eventually they started adding different objects and even animals into the equation. And the results looked pretty impressive. Frame matching is very effective, but where the match cut just really goes to another level is by combining action shots. The way this works is the motion from clip A is cut midway through and continued in a very similar way in clip B. With image segmentation, we're only taking one frame basically and kind of matching that way. So how do we do it with actions? Well, luckily, there's actually already a way you can do this with computer vision called optical flows. Optical flow takes every pixel of an image and then creates a heat map based on what has moved the most between the previous frame of the video. So Netflix would take a shot, calculate the optical flow, average it out into one image, then use this to search for matches. And what they got back was not really what they intended. Remember, these action shots were to grab items of interest, moving in one way or another, transitioning over into another action. But instead, they found that the matches were matching based on similar camera movement. So these findings were interesting, but how do they package it all together? Well, they did it in 5 steps. First, shot segmentation. A scene contains a collection of shots. A shot is a sequence of frames between 2 cuts. Remember this because we're going to go over it a lot. There are lots of open source models that can detect this, even a Python package, surprisingly enough. So everything needed to be broken down and grouped by shots. Step 2, shot deduplication. Think of a talking scene for a second. You often have 2 characters in the same shot going back and forth. So Netflix would take the beginning frame of each shot and convert the frame into an embedding, which is a mathematical way of representing an image or any data point. This way, it could detect how similar it is to other frames. If the shots were too similar mathematically and was in the same episode or movie, chances are it was a duplicate and was filtered out. Step 3, compute representation. This step determined what type of algorithm was needed to do the match cut, the optical flow, the image segmentation, etc. Step 4, compute pair scores. A similarity score is given to each pair. The higher the number, the more similar they are. Step 5, extract the top results. They then take the top results based on whatever criteria they're looking for and hand off to the editors. And this would save hundreds, maybe even thousands of hours of editing time because you often had to go through a large catalog of videos just to find that right moment. But wait a minute, search for videos. How do I even search in this large catalog for videos specifically? Search. It's something we use every day. Enter a query and return matches. This works really well with text, but what about for videos? How can I search for a specific thing happening in a video? If I type in a query, how does that get represented in video format? I have no idea. At first, an attempt was made by the Netflix engineers to use the segmentation method like in the match cut segment, but found that it wasn't specific enough. For example, in Stranger Things, a Demogorgon wouldn't be recognized as a Demogorgon and would be pretty hard to search for otherwise. Like, how do you even explain that thing? The good news is that they technically already found the answer: embeddings. They had pre-trained image text models that created an embedding space between the two. That way you can see the relationship and similarity between the two. So Netflix extended this model to include video sequences that could also include a text pair from pre-existing data. They used something called ray train to train the model at scale while using dcord to decode videos much faster. Netflix then used these segmented videos with text pairings and embedded them, putting them in a database at the shot level. And remember, embeddings just means that they can turn something like a video, text, image into a mathematical format. And since embedding is really fast, what you can do then is enter a search query, and before it even hits the database to compare or query, you can embed it and do a cosine similarity to get the desired result. They actually use this as well in the action sequence that I talked about before, but here's how cosine similarity works. Cosine similarity measures how aligned 2 vectors are by calculating the cosine of the angle between them. This sounds complicated, okay? I'm sorry about that. It confused me too. But essentially what this means is that you can determine how similar items are to one another even though they don't match. So for example, the phrase, "Can I get a peanut butter sandwich?" and "Is there a food that contains nut spread of some sort?" which I wrote that in the script and that is just a really weird thing to say. They would both be close to one another. Netflix already had a huge catalog of shots that were labeled like this, like close-up or panning shot. So this gave them a significant head start in training this model. So to recap, Netflix was able to take text and video pairs and convert them into a mathematical format. Then a search query was able to be converted into the same format in order to determine how similar it is to the shots of a scene. So if I search exploding car, a bunch of clips of exploding cars would come up. If I searched fantasy gremlin, that would probably pop up too. Now, remember when I said shots and scenes? How do we even determine when a scene has changed? Now, we already discussed the difference between a shot and a scene, but to recap, a shot can be pretty easy to understand visually. A sequence of frames that plays before getting cut to another shot. But a scene is a collection of these shots, usually with the same narrative, tone, pace, whatever. And that's kind of the issue with this concept of a scene, at least from a computer vision standpoint. It's a bit too nuanced. There's a lot of things that can just make a scene up. Let's take the scene from Into the Spider-Verse. Visually, all the shots line up in color matching, mood, dialogue, and pacing. However, when Miles gets bit by a spider, we see a huge change in how the scene works. For us, this change is obvious, and we can still identify it with this scene. But a computer might see a scene change, at least based on the previous algorithms we mentioned. The colors have changed, the music has shifted, the tone has just shifted in general. So Netflix made two different ways to determine when a scene change happens using frames. It's pretty awesome. The first, leveraging aligned screenplay information. A screenplay is written to allow producers and directors to execute a written piece on the screen. Unlike a book, the screenplay is written with explicit visual instructions to how it should look and sound, kind of like a program for a computer. Okay, I'm sorry. That was me trying to, remind you that this is a coding channel. Sorry. Since screenplays are written like this, it's actually fairly easy to parse using optical character recognition technologies. But here's another issue. Netflix needed to find a way to align the screenplay with the closed captions of the movie. But the movies that we often see differ a lot from the screenplay that is written. Actors go off script all the time, and sometimes scenes change. In fact, Matthew McConaughey uses the screenplay as a suggestion rather than the source. But we've already found a way to deal with this type of thing though. Embeddings. Remember, mathematical representation of something? I think you get it by now. If we embed the screenplay line and the dialogue being spoken, we can use paraphrase identification to get the closest match. When we talked about cosine similarity in the last section, we actually kind of already talked about paraphrase identification. This software is also used to let chatbots understand your general wants. Play music in the shower means play Spotify in the bathroom speaker, etc. And this is where dynamic time warping, or DTW, was used. DTW is like a sophisticated matching algorithm that helps Netflix line up screenplay content with what actually appears in the video, even when the timing isn't consistent. So think of it this way, if we have two sequences, the screenplay text and the actual dialogue with timestamps, aka the closed captions, in Netflix's case, they create a timeline connecting all of the lines that match, or don't appear, or are delivered late in the dialogue. Dynamic time warping helps find the best way to warp or stretch one sequence to match the other. But how many times have you watched a movie and sat there with the screenplay and been like, I don't know when the scene has changed? People don't do that. It's actually kind of weird. So how do we identify that without knowing the screenplay? This brings us to the second method, the multimodal sequential model. We're bringing back the good old frame analysis models. Going back to the shots, they used bidirectional gated recurrent unit networks. God, that word was just scary to say. Let me explain what that is. A gated recurring unit, or GRU, is like a memory cell that helps the AI model remember important information while forgetting irrelevant details. In the case of a shot sequence, the model would have to guess what happens next based on what it's already seen. So this makes scene detection basically impossible. And that's where the bidirectional comes in. It processes it from beginning to end and vice versa. So the model knows what's in front of it as well, aka the frame. You see what I'm talking about here? So Netflix then separates the video and audio from each shot. They then take the audio and separate the dialogue, the background music, and sound effects, and this gives the model better clues to identify when something has changed. They then embed all of these video and audio tracks. Then when they run the model, they're able to beat some of the better open source technologies that exist by sometimes over 3 to 7%. Thanks to all the engineers that contributed to the models, as well as writing the articles on the Netflix tech blog. Without them, this video wouldn't exist, and we wouldn't learn about some of the cool ways that computer vision is powering editing, analysis, whatever. I've linked them in the description below if you want to read them and get a better analysis out of this, but honestly, it's just so epic. I also have another video that talks about how Discord handles the world's largest server, so make sure you go check that out as well. Peace out, coders.